Welcome to This Explainer. We're diving straight into a massive topic today, traveling from the fundamental mechanics of theoretical computing, the actual engines that make algorithms possible, all the way to the absolute mathematically proven limits of what a machine can do. If you've ever wondered where the hard boundaries of technology actually lie, you are definitely in the right place. Here is our roadmap for today. 1. Meet the Turing machine. 2. Upgrades, multi-tape and beyond. 3. The universal Turing machine. 4. The unsolvable halting problem. And finally, 5. The true limits of computing. All right, section 1. Let's meet the Turing machine and look at the foundational components of theoretical computing. So before we push to the outer limits of computing, we really have to start at the bedrock, the deterministic Turing machine, or DTM. Now, what makes this model so incredibly powerful isn't the physical idea of a tape, but its strict reliance on a specific transition function. It's totally deterministic. For any given state and symbol, there is exactly one pre-programmed action, no guessing. And that strict determinism is exactly what lets us apply rigorous engineering principles to solve complex logic mathematically. And because it's so strictly deterministic, we can actually verify and validate the correctness of this machine through a highly predictable sequence. You just validate the state transitions, apply that transition function, and execute the tape movements. By running these exact sequences against known computational problems, we get a mathematical guarantee of the machine's correctness without any ambiguity whatsoever. Moving to section 2, upgrades, multi-tape and beyond. Let's explore some design alternatives for efficiency. Now, a single tape machine is theoretically powerful, sure, but practically, it introduces massive inefficiency for complex operations. So we upgrade to a multi-tape design. By separating the input, the working memory, and the output, we drastically reduce the time complexity of our algorithms. Comparing these models is how we identify the absolute most efficient computational architecture for specific classes of problems. But the upgrades go way beyond just adding more memory. We also contrast deterministic models against non-deterministic ones. You see, an NDTM doesn't just plod down one strict path. It can actually branch out into multiple computational paths simultaneously. Now, our physical computers are deterministic, obviously, but we use these NDTMs as a crucial theoretical tool. They help us evaluate problem complexity and really map out the boundaries of efficient computation. Which brings us to section 3, the universal Turing machine. Literally, the machine that simulates all machines. I want you to imagine an architecture that encapsulates all those previous models we just talked about. The universal Turing machine takes the description of another Turing machine, its rules and its input, and just simulates it. This right here is the theoretical grandfather of the modern general-purpose computer. It completely proves the stored program concept. You don't need to build new hardware for every new task. You just load new instructions, and boom, the machine fundamentally changes its behavior. But man, this brings us to a massive theoretical crossroads. Think about it. Since a universal Turing machine can simulate absolutely any software, does that mean it can solve every computational problem? If we give it infinite memory and infinite time, is there anything an algorithm simply can't figure out? Let's look at section 4, the unsolvable halting problem. This is where we hit the unbreakable wall of computability. The answer to our big question earlier? It's a mathematically proven no. We hit a hard wall known as the halting problem. It asks what seems like a really simple question. Can we write a program that analyzes another program and perfectly determines whether it will eventually halt or just run forever in an infinite loop? This formal statement defines what we call an undecidable computational problem. It proves that certain logic puzzles simply cannot be resolved by computation. To prove this undecidability, computer scientists use a diagonalization argument. Now, without getting bogged down in the heavy math, it basically works by contradiction. If you build a theoretical machine that supposedly solves the halting problem, you can feed it a paradoxical input designed to do the exact opposite of whatever your machine predicts. Because of this inherent paradox, the conclusion is absolute. No single machine can solve this universally. There are strict, hard limits to computation. Finally, section 5, the true limits of computing. Let's compare these models and see the real-world implications. When we map out the taxonomy of these computing models, we see some really clear trade-offs between expressive power and limitations. Down at the foundation, finite automata handle simple state-based tasks. Think traffic lights, but their memory is incredibly limited. Move up a step to push-down automata, and you gain stack-based memory, which is perfect for parsing programming syntax. But even at the very top, with the vastly expressive power of Turing machines, we still smash right into that ceiling of undecidability. You might be wondering why undecidability actually matters to software engineers today. Well, these concepts serve as the direct grounding for modern applications. Because we understand the strict limits of computability, we know exactly when to stop wasting time trying to write a perfect algorithm that solves the unsolvable. Instead, we pivot. We write algorithms that approximate a good enough solution, allowing us to evaluate design efficiencies and tackle incredibly complex problems in fields like AI and cloud infrastructure. So, we've journeyed from a fundamental theoretical model governed by strict transitions to an architecture that can simulate any software straight into a mathematical wall, proving some things are just forever beyond a computer's grasp. It leaves us with a pretty critical question to wrap things up. If there is a mathematically proven boundary to what the ultimate machine can do, what impossible problems are we trying to solve today, and how will we engineer our way around those limits? Thanks so much for joining this explainer.